Ruth. I'm Innovation Lead for Circular Economy at Innovate. So, as most of you know, we have helped sort of co-fund the NICER programme, but we've got a very specific role within it as well. So we're here to cover what is the Innovate bit and specifically the link to getting SMEs involved in the programme. So since it's not always clear that everybody understands how UKRI is actually put together, this is just for the clarification of things. So we used to be entirely separate to the research councils, and the research councils, obviously, what's mostly familiar to academics as providing most of your funding. But Innovate was incorporated to kind of show that it is a nice big family of where research and innovation happens. But we are the bit that's business facing. So we are there to acknowledge that there is a space for how do we get the things from academia into industry and into business, but also saying that not all research happens in academia. A lot happens in business. So how do we provide that direct-to-business funding to make that happen? A bit of context to kind of how NICER sits alongside other things we're doing in this space. So I'm part of the materials and manufacturing team within Innovate. As I say, although I kind of lead on circular economy, a few of you will be aware of other programs that we do. Basically, I'm not the only person that does circular economy things within Innovate, even if I'm the only one with it in my job title. So you'll be aware of the Transforming Foundation Industries programme, which does an awful lot that is fundamentally about circular economy, resource use, targeted at the foundation industries. We've also got the very specific Smart Sustainable Plastic Packaging programme, which is looking at this space and obviously some very key sustainability and circular economy drivers there. But we've been looking, how would you sort of tackle this from an umbrella point of view? And actually a piece of work that's only gone live a couple of weeks ago is our Vision for 2050, which is about reimagining materials and manufacturing. Importantly, this is a framework, it's not a static document. So we proposed a framework for how we actually update the picture on this space. Now, I'm not going to go into much detail because I want to give plenty of time for SMEs talking today, but just saying circularity is in there at its heart, and it isn't just in the recycling piece. We've got a lot on these tighter loops of circularity in there. But essentially our core areas are everything from future economy materials that also take circularity into account, not just materials for new materials' sake. The design aspect within making things, and also noting that's not always done by people with designer in their title. Engineers do a lot of designing in the actual space. Resilience of supply chains. We sit under a net zero domain, but a lot of what we're doing is about creating resilience for the UK manufacturing materials sectors, not just about sort of our contributions towards net zero. But world-class production, we are about sort of trying to get innovative things there. So this report, if you are interested, yet another QR code. But this, as I say, is a framework. We'd welcome views on it, we'd welcome further inputs, but it does show kind of pathways to where we need to go. And over the next 2 years, we'll be doing a lot more work to try and test some of those assumptions so that it gets regular updates and, as I say, it doesn't just become a static document. Give you a moment there while those phones are. Okay. So now onto the NICER programme and other people talking. So just that clarifying where we sit in this. So I assume a lot of this was said yesterday on sort of the overall sort of NICER programme and vision. Innovate isn't solely in this bubble, but we're very much in this bubble of making sure that research that happens in these centres actually gets into business, but also, as I say, research and innovation that's happening in business is getting into the programme. So specifically within the £30 million fund, we had £2.5 million to enable SMEs to participate in the programme. So the companies who are here today are from round one, where we had £1 million worth of funding. And as we've heard, there are some who are successful in round two, which is £1.5 million of funding. So on to the projects. So today we've got delightfully managed to get 4 of our projects here. So thank you very much in advance for coming today. And what I'd say is it's quite an interesting space, the chemicals one, because compared to all the other centres who had much more kind of specific sort of materials, the chemical space kind of it resonated differently with business, let's say. Some were very much had sort of olefins and polymers at their heart. Others were, how do we use chemical technology and chemical sort of innovators to help with other problems? So, when Djelloul's speaking later, you'll see his project could have just as well sort of associated with the technology metals area, but it's interesting to see how that expertise from the chemical sector can be used to solve problems in other sort of circularity spaces. So I'll come on to them sort of as we go through, but we'll just sort of kick off right away, really. So if I can welcome first Ruth Bowley from Hexigone, who I've been looking at circular inhibitors removing corrosion sustainably. It's a catchy title. What I want to say about this one is this is a real good exemplar of if you're an enthusiastic SME already producing a very sustainable product, but you want to bring in more circularity. How on earth can you do that when a lot of the players in the space are big multinationals? So, thank you, Ruth. Over to you. That button to progress.
Hi, so I'm Ruth Bowley, and I work at Hexigone Inhibitors, and I am the Quality Control and Research Manager. So we manufacture paint additives, anti-corrosive paint additives, and our product in Telean uses ion exchange technology, so that when our product's added to a paint and there is a corrosion site, so maybe a scratch in the metal, our product then will move to cover that metal and protect it. The company is about 5 years old. We've been selling for the past year and a half or so, and we've been granted 3 patents in various regions globally. So it was initially developed to replace carcinogenic hexavalent chromate. Chromate, or chromium, was sort of brought to public attention in the film Erin Brockovich, where a small town in the US was actually had their drinking water polluted by a local energy company, and the actual chromate is very toxic, very carcinogenic, but also very good at inhibiting corrosion. So it's been used widely globally for quite a long time. The EU has legislatively banned it since 2019, and that ban's slowly rolling across the world because so many people are actually being hurt by this chemical. So corrosion, it actually costs the world economy $2.5 trillion a year and is responsible for about 3.2% of global CO2 emissions. That's purely steel manufacture to replace corroded steel. So it actually has quite a large impact. So you can see it's about almost 50-50 chromates and their now replacement, which is mostly zinc phosphate. The coatings industry has actually struggled to replace hexavalent chromate and find something quite as effective. So zinc phosphates, they do work. They do have environmental issues associated with them. They're manufactured from raw material that's now on the EU critical materials list. When they're in paint, they can actually slowly leach out over time, which has an impact on the environment and an impact on how good they are at inhibiting corrosion. If you've painted a boat with paint that contains zinc phosphate and it's leaching out into the ocean, and that might affect acidity in the ocean, it actually has quite a lot of impacts. So they're a direct competitor to us. So our product in Telean does not use any critical materials, and it allows manufacturers to remove environmental hazard warning labels associated with anti-corrosive additives. So the project we were funded to look into was to source and test a raw material to replace one of our current ones. So about 60% of our product is made of this resin, which is olefin-derived. It's actually widely manufactured as part of a different industry. So it's quite easy to source, but we were sourcing as a raw virgin material, and 60% is quite a lot. So we were looking into alternatives. So we contacted this large multinational chemical company who was actually disposing of out-of-spec products. They'd made it for this other industry, and it hadn't quite met the spec. So they were just sending it to landfill, or their environmentally friendly version, which was burning it to power their factory. So we said, well, we can take some samples off you, see how they work. They sent us, I think, 4 or 5 samples, and we found that one of them was actually chemically identical to the one that we needed. So we were looking closely at that one, but we didn't know that the structure was quite right. We were checking for contaminants. Like, technically, this is a waste product they had. We didn't want any contaminants affecting our final product. We need to know that the active ingredient would go into the material, and if it was easy enough to process. Scale-up is quite tricky. But we discovered that actually it absorbs more active ingredient than the resin we were previously using, and it is okay to process, almost as easy. So we're balancing that out, and it's quite nice having the flexibility that if we wanted to increase the active ingredient, we could. One of the big challenges to overcome was time. I think this is the same with every project, but we were shipping, this company was in Japan, so we're shipping 200 kilograms. It would take 3 months to arrive. We would test it, which would take about a week, bit of QC, another week, and then we'd order another 3 tons of material for a full-size test. So yeah, just waiting for the material to arrive took the longest. And I thought, well, our original material was actually made in the UK. Is it actually better to ship it from Japan, even though it's a better use for that material? So we did a life cycle analysis, hesitant to use the word now, and there's a lot of strong opinions, but it was from cradle to gate we did this. So as soon as it left our factory, that's where we stopped the life cycle analysis. And it said that, yes, it is actually better to take this material away from landfill, away from incineration, and use that instead. And the other big challenge was to convince this large multinational chemical company to admit they actually had a waste stream. They did not want to admit to that. But the way we got them to say, actually, yes, we do have this, is to say it's actually got value. They were less interested in the fact that they could take responsibility for their waste, and more interested in the fact that they could actually have assigned waste a value. They previously had to have it paid to be taken away, and we would then pay to take it off them. And then finally getting that into the country. Customs is not happy when you import industrial waste. So we had to say, actually, it's not industrial waste. We have paid for this. It's a raw material. And then it was fine to do that. So now our study is complete, or it will be at the end of the week. We're putting in place commercial agreements to make sure that material can come to us. So we've got a stable recycled raw material for us and product stewardship for that manufacturer. And then because of our patent, we are the only company that can use this particular route, so turning into the corrosion inhibitor to recycle the material. So we're using 60%, but technically up to 75% of our product could contain the resin. But we're only supplementing in about 22% recycled content at the moment, because there's actually a limitation on how much of that material there is. It is an out-of-spec material. It's not made for us. So we're looking at other avenues to get material. So future products could be that the material that was in spec goes to a customer. It has a lifetime of about 4 to 10 years, and then it can be disposed of. Or they might be able to regenerate it and give it to us. A lot of it's going into the food industry. Regenerating stuff in the food industry and reusing it's not so easy. But we're not bothered about that. It's going into paint. So we're setting up some NDAs, and we're ready for that. And then, it's also good to note that paint systems, which are quite tricky to recycle at the moment because there's a lot of heavy metals in there. If our product's in there, there are no heavy metals associated with that, and it should be easier to recycle. We don't do the recycling, which would be nice in the future, but hopefully further down the line that would be easier for a company that wanted to do that. But yeah, anyone have any comments?
So just if there's any specific questions, we could probably take sort of one now, and then we'll everybody will come back at the end for a sort of a general discussion. So are there any quick questions? We've got one there. There you go.
How did you identify that they had a not waste for you to use?
That was our CEO. I'm not actually 100% sure how he was doing it. I don't know if he managed to Google it or if he met someone at a conference. But I'm not actually sure on that one, sorry.
Go on, it's a quick question. I'll have a second one though.
How challenging was it to declassify it from industrial waste, and sort of what was the process of actually declassifying it?
Yeah, it was actually talking to the company, and they would, instead of sending it off as industrial waste, it would leave their site not as waste, and leave their site as product. So it was actually assigning value to it.
But I think that's sometimes the case where some people kind of see a waste and go, oh, I can have that for free. But actually trying to get something for free from a company because it's a waste actually creates more barriers than if you actually say, we'll give you something towards it, because then it's much easier to see how that's a product. So sometimes companies do that in order to make that clear that this is no longer a waste.
Even if it only costs a penny.
Yeah,
it's still
token costs sometimes. Okay, great. Thank you, Ruth. I will move on because I want to give plenty of time for things, but thanks again to Ruth. So next we have Rheon. Is Sarah here? That's it. I'm delighted to meet Sarah because of the other three projects I've been kind of the innovation lead for, but my colleague's been the link to all this project for, so I haven't met Sarah before, but
nice
delighted to meet you.
Thank you.
Yeah, Rheon, what great to see you though about this project is this is a really good example about how it's very easy to put sort of various plastics all in one box when we do our Sankey diagrams and say this can all be recycled, but with Rheon, they've got a very high value material, and this really shows the example of actually you don't want to lose some of that high value by just lumping it in with everything else. So seeing what they can do on a closed loop recycle.
Thank you, Amy. So thank you very much for inviting me. I'm Sarah. I'm the Chief Science Officer of Rheon Labs, and I will give you a bit of an overview about what we do at Rheon Labs and then come a bit to the project so it has a context. So every now and again, a new material is discovered which has a completely different set of properties. And that defines not only a new application, but a completely new market. And this was, for example, the case with Gore-Tex, with the first breathable textile, Lycra with the elastane market, and Kevlar. And similarly, Rheon is a whole new set of properties. So Rheon is a very high energy absorbing polymer, which is strain rate sensitive. And what that means in simple terms is we have a polymer that is soft and flexible in its natural state. However, when this is subjected to force, it stiffens up. And for example, this can be used for brain protection, so for helmet applications. And here we can see an NFL helmet, which was one of the applications we worked on. So we are one of the winners of the NFL Helmet Challenge. And in this case, the Rheon technology was a combination of the polymer with engineered three-dimensional geometries, which have been specifically designed to protect the brain from both linear and rotational impact. So usually, brain damage is caused by a combination of linear and rotational impacts, and conventional materials can protect you from both. Rheon, with the geometry and the material, can protect you from both, and we can have over 10,000 life-threatening impacts before the performance deteriorates. Another similar example is body protection, so body armor, for example, for the motorcycling industry. So we have worked with Harley-Davidson on body armor, and the problem here is usually body armor is stiff and protective and quite bulky. So it wasn't supposed to have sound. I'm very sorry for that. There we go. But you can still see the video. So, and in this case, we developed a very thin, flexible, and comfortable body armor, which is breathable. And here you can see how it is impacted with a high impact under a block of ice, and the block of ice survives. So those are impact protection applications. Our newer applications go towards dynamic support. So for example, the easiest one I think to understand is a sports bra. So sports bras are either comfortable and soft and nice to wear, but they don't provide support, or if you want support, they're stiff. So support is induced with stiffness. And the strain rate sensitive properties of Rheon allow us to design a sports bra which is soft and comfortable under low loading regime. So when you're just walking or sitting, it's soft and comfortable. However, when you load, so when you run, sprint, it stiffens up and provides you the support you need. And that's revolutionary for the sport market. And we have just launched the first responsive support application with Adidas last week, and with leggings, so muscle support to specifically control muscles. And currently, the Rheon technology is available either as injection molded components or as film. And in this project, I will talk about our 3D printing applications as well. So Rheon is a thermoplastic polymer material. It's not one polymer, it's a combination of multiple materials, which comes as pellets. This is injection molded to parts, and in the injection molding process we create waste. So first the sprues, which are common to all injection molding processes, but also parts which just don't pass QC. And it's quite important in our case because of the helmet applications, for example, parts need to conform and with quite high quality standards. And in this project, we looked into ways to reuse this waste from injection molding and to upcycle it, in this case for 3D printing. Rheon waste is not that easy to recycle using conventional methods just because it's very soft. So you need to find a methodology to actually regrind that back into a usable format. And you can't just recycle it using conventional recycling streams because of the complexity of the material formulation. So we looked into two different 3D printing methods. So one of them is fused filament fabrication, better known as FDM. And in this case, you have a filament which goes through an extruder, it's melted, goes through a heated nozzle onto a platform, and you print an object layer by layer. So we looked into this, or we approached this from two different angles. The first one was hardware development. The material is extremely soft and therefore tends to buckle. So using conventional hardware for 3D printing Rheon is not possible. So we redesigned a whole new print head and nozzle with a cooling system and a direct drive to actually be able to print this. And also we worked on material development, so optimizing the mechanical properties of this waste stream, the filament thickness, and the flow properties, which play an important role. After a variety of technical challenges, which are shown here, we managed to actually get a material which prints fairly nicely, shown on the video on the right. And in this case, one of the things that we studied is, how does 3D printing compare to injection molding? So can we actually use these 3D printed parts as a model for our injection molded parts? And also, how do different percentages of recycled material influence the mechanical properties? Of course, we optimized the orientation and infill pattern and all sorts of technicalities around. And what we saw here is that the amount of recycled material does not have an effect or no significant effect on the mechanical properties, which is great. So, or on the hardness, or on the specific energy transfer, so the impact performance. And here we can see at the upper part, we have some three-dimensional parts. The three-dimensional parts, and those are typical of the Rheon technology. So those are applied in different applications and showcase really not only whether 3D printing would be a useful model system for one type of application in Rheon, but for a variety of applications. However, fused filament fabrication is quite slow, not very accurate, and gives a bad surface finish. So it's great for prototyping. So we can, if we have a new geometry that we are designing, we can prototype it and say, okay, this would work for this application or not. However, for manufacturing purposes, it is not suitable. So for a customized Rheon range, selective laser sintering is the right way to go. So in this case, you have a polymer powder which is selectively sintered using a laser, layer by layer again, and usually you have a refiller roller. And as you can see here, this is a print farm with big industrial 3D printers used for actual manufacturing purposes. And that was a challenge for us. So our first challenge was, how do we actually get a way to screen material formulations rapidly and assess what works and what doesn't work. So we adapted the hardware to have a very small area to allow for a fast screening of material. And of course, we had to also work on the formulation, but before the formulation, on actually getting a powder that is suitable for SLS. So we chose to go with an ultracentrifugal mill and look into cryogenically frozen material, which we then milled down to 80 microns, which was suitable for SLS. And there are quite a lot of challenges when you actually look into selective laser sintering. So one of them is, of course, particle size distribution, but mainly particle flow. We optimized a lot of the formulation, and we worked also here with high percentage of recycled material, and we managed to get a proof of concept, which needs some further development. So what are the future challenges here? We talked about injection molding waste. However, our film business creates a significantly higher amount of waste, which is more difficult to process because it is a film. It's difficult to reuse regrind, reincorporate into the production process. So how are we going to address that? And just to say, it's 40% of waste at the moment, and that's already reduced. The problem is that the patterns, the engineered patterns that we use for laminating onto textiles are really important for the performance. So reducing the waste would mean using a different pattern which doesn't allow for the performance. So rather than trying to change the pattern, it's how can we actually reuse these materials? So that's something we're actively working on. And the scale up of our selective laser sintering, as well as the use of biosourced or post-consumer recycled raw materials. That's something we are actively investigating at the moment too, and which represents a big challenge. In addition to that, that's something that's not written here, is end of life. So how are we going to address the end of life of, for example, inserts in helmets or material which is heat laminated onto textile? Yeah, with this, thank you. I'm happy to take questions.
Yeah, really super. That just kind of, as I say, trying to see how to sort of do recycling within the sort of the factory gates. Really is good. Any quick questions for Sarah, or things to wait till the end? Oh, got one.
I guess the obvious question is, why didn't you recycle it back to the injection molding process?
Very simple. You're not allowed to import waste into China, so that's one of our biggest challenges. So. Reground material, recycled material. So we are, our production sites are a bit all over the world, and from the logistics, we would need to import that into China. It's not possible. It's considered waste material. That's the first one. The second one is the shape of your pellets, which basically we have carried out trials with the injection molding process. And in that case, you become so much less efficient because your pellets are not perfect, that it's just not sustainable from a manufacturing perspective. So 2 reasons.
Okay, thanks. Okay, so we'll pick up some more in a bit. Thanks, Sarah.
No worries.
Okay, our next presentation is Djelloul, who, as I say, this project could have sit somewhere between the chemicals one and the tech metals one, but I say is a great example of sort of chemical technology. Taking something that's sort of been known at an academic level, but actually how can it be further optimised when you throw some more engineers and specialists at it? So thank you, Djelloul. Yeah, that one on the right. This one there. Okay.
Hello, and thank you very much for inviting us. The project is to look at the feasibility of applying ultrasound to recycle valuable metals like lithium, cobalt, and other metals used in lithium-ion batteries from waste lithium-ion batteries. I'm sure that most of you are familiar with the importance of and the difficulties of recycling lithium-ion batteries. And I think that from what I have seen so far, I think our company is the odd one out, because our background is not recycling, but it's something else, as I will explain later. But we would like to use our expertise and know-how to apply to recycling. So my name is Djelloul Seghier, and I manage R&D project at NDT Consultants. So what I'm going to talk about in this presentation, I'm going to introduce our company, and then give a brief overview about the project that we worked on and some results, and then I'll speak about some challenges that we found in this research. So our company is NDT Consultants, and as its name indicates, we are active in non-destructive testing, which means we look at defects and cracks and in materials and industrial procedures, and also analyze some materials using some non-destructive methods. So the company has been established in 1985. We are based in Coventry and in Bangalore, India. We are involved basically in all aspects of non-destructive testing, which means consultancy, training, and inspection of parts, both in-house, in our premises, and on sites. And we have a team of R&D that designs and develops some products that our company manufactures and sells. And we also sell some high-tech NDT company to the NDT market. Quickly, in terms of level 3 consultancy, we are involved usually basically in aerospace, energy market, automotive, and defense. We are retained by many clients, both in the UK and in Europe, Asia, and in Africa. We are also approved in terms of training by the big players in the NDT market, which are Rolls-Royce, Boeing, and Airbus, and others. We, in addition to normal consultancy in NDT, we also provide consultancy for clients and customers that come and see us who have a new product or new industrial method that for which there is no existing non-destructive testing procedure. So we try to develop a new one for them or adapt an existing one. In terms of the core techniques that for which we have expertise and facilities in our company, we have basically all the conventional non-destructive testing techniques such as X-ray, infrared thermography, ultrasounds, about which I'm going to speak for this project, eddy current, and we can say all the conventional NDT technique. We use them both for routine inspections of parts, but also we use them in R&D to develop or adapt new NDT techniques for new applications. So the problem that we wanted to add our contribution to, it's quite a known problem, which is how to recycle lithium-ion, the valuable metals, the expensive metals such as cobalt, lithium, and manganese, how to recycle them from waste lithium-ion batteries is quite a known problem, and there has been a lot of discussion on it. We all know that you all know that lithium-ion batteries are being increasingly used in several sectors of the industry, including electric vehicles. And as we are told that in the next decade or so, there will be an exponential increase in the usage of electric vehicles. So therefore, it is expected by around 2030, there will be around 2 million metric tons of waste lithium-ion batteries. Lithium-ion batteries, they are used for 8 or 10 years in electric vehicles, and their capacity goes below 80%, for which they can no more be used in an electric vehicle. So either they go to waste or they are repurposed. However, the problem is, this is all good, everything is becoming electric, but at the moment, it looks like less than 5% of the waste lithium-ion batteries are recycled in Europe and America, and even less than 2% in some other places in the world. And there are several reasons why this very low rate of recycling. Some of them are economical, some of them are technical, but we can summarize them as follows, safely. The two techniques that are used to recycle lithium-ion batteries are pyrometallurgy and hydrometallurgy, where batteries are filtered and then they're shredded. The electrode material is shredded into small powder or small flakes, and then which we call the black mass, And after that, this black mass is subjected to very heavy chemical processing to leach, to separate the different components, which are the metals involved in the chemistry of the battery. So this this chemical process involved in recycling this, they are very hungry in energy, so very costly. They're very complex, and they use some polluting materials such as sulfuric acid to leach the material. So this is one of the reasons the industry does not use them, because they are quite expensive and it's cheaper for them just to use new raw material to make new batteries than to recycle the waste ones. So a lot of experts think that now it's the time to take seriously recycling of lithium-ion batteries in anticipation of the increased usage that will happen in the next years. And this is where we wanted to add our break, at NDT Consultants. As I said, our background is not recycling, but we know ultrasound. We are an NDT company, so we have expertise in ultrasound, for which that we use in a lot of, in many applications, both as NDT technique, but also for cavitation and for other applications. So how we intend to use ultrasound to recycle these valuable materials from a waste lithium-ion battery. The first step is that we use ultrasound on electrode material to extract the active material, which is the lithium, cobalt, manganese, or depending, batteries have different compositions, but let's talk about, for example, simple battery, which is cobalt, lithium cobalt oxide. Then this active material is bound to the electrode metal using an organic adhesive, and this one is very strong. And one of the reasons the recycling methods now shred the whole electrode is because it's difficult for them to break that organic adhesive that binds the active materials to the metal. So with using ultrasound, we are hoping to use just a very mild, solvent or any liquid, and ultrasound will be used as a catalyst to dissolve that organic, binder between the active material and the metal. So we plan to use ultrasound. We plan to use ultrasound in this case, either just ultrasound with a resonance frequency for the organic material to break the bonds. And also, we want to use ultrasound to produce cavitation. As you know, cavitation produces a lot of pressure, a lot of temperature in a liquid. And this pressure, mix of pressure and temperature, will break the chemical bond of the organic binder. So once we have delaminated the active material from the metal electrode, the next step is to leach, if necessary, leach the different metals from the oxide, separate them from the oxide and produce some salts, which the current technology that are used do as well, but they use very corrosive and very strong acids like sulfuric acid, and they heat at very high temperature. But by using ultrasound, what we can do is that we can do this at very low temperature, so much less energy used, but also we don't need to use so strong acid like sulfuric acid. We can use just simple organic acid like citric acid, for example. So 2 steps: delaminate the active material from the electrode, and the second one is to leach these valuable metals that we want to extract from the oxide. how many minutes I have left? How many? Oh my God. Okay. So the step that took so much time of our time is to design and manufacture the right ultrasonic transducer. As you can see here, we used one variation of ultrasound, which is called magnetostrictive transducers. So we have to, in order to make the right transducer for a given application, we have to calculate the parameters of the coil and the magnetic field, the permanent magnetic field, as you can see here in this picture. So I'm going to go through these details. Sorry, okay. So we designed and manufactured some ultrasonic transducers, and as you can see in this picture, we have this big black box is the power supply, and this and this the container there is contained with solvent, and where we put the electrode material in the liquid, and the ultrasonic small black box with the white sticker is the transducers that we developed. So that will create cavitation or ultrasound, and this will delaminate the active material from the electrode. So briefly, I'm going to show you here. So as you can see in this picture, on the right side, you have a piece of this electrode material that we cut from a Nissan battery, leaf battery. So you can see the black material there is the active material, and it is bound on a piece of aluminium. Once we have treated we have treated this with ultrasound. On the left side there, you have the aluminium foil, which is very clean, which means we successfully removed the active material, which is in the middle there. So in the middle there, we have the active material, which is the mix of the valuable metal that we want to extract. And here on the right side here, we have a comparison between, on the green side there, is the efficiency of the delamination. The green one is when we use ultrasound, while the red one is when we use just the solvent, the chemical, without ultrasound. As you can see, there is a big difference here. So we are trying our method on both whole electrode material without shredding, but we are also trying to be realistic. We know that in the industry there is already some procedure in place where batteries are shredded. So we are thinking, if our method were on a whole electrode cell, can it also work on a black mass where the electrode material has been shredded into small particles? So we are trying to scale up our method and use it. If we are able to do the same thing on the black mass, that I think this will be a very good plus for our project. So I just want to make a last comment here, because we are not from the recycling industry. We were not familiar with we were not expecting some challenges. So when we were working on waste, because we were going to work on waste batteries, we knew that we need a trial permission. So we talked with the environmental agency. We were told that it takes few weeks to get the trial, but it took around 1 year. But luckily, they said yes, you can have some waste cells, 1 or 2 in your company, and do some tests on them. But it took 1 year for us to have this permission, this trial. I thank you very much.
Thanks, Jill. I think one of the interesting things for me about this project is, although kind of using ultrasound in this sort of space has been known for a while, the degree to which you can optimise kind of the process so much further on design of tanks and shapes of things to actually get that power level down significantly on sort of to make the scale up feasible was a really big thing for it. Have we got any quick questions? Otherwise, we'll move on and come back to this in the panel. No. So thank you, Djelloul. Okay, thank you. Right, so the final one of our 4 projects from this round is Medicycle. So we've got Bev here today who's going to talk to us about, this is another one, a bit like the Rheon one, of where we got some really high value plastics that are just missing out on either being, not even being reused, not even being recycled because of the operating environment, literally, where they are. Thank you, Bev. It's that one to progress.
Hello everyone. So excuse me, I'm going to read from my notes because I'm not massively well prepared, but I'm sure you'll forgive me. It's the last one today. So our project is really it's born from our own product, which we make anaesthetic drug trays for use in theatre. These are all made from plastic, so we needed to find a positive end-of-life solution for our own product. So very much on a similar theme to you've been hearing already. So our project addresses the challenge to create a disruptive process that will provide a safe route for recyclable medical plastic waste out of hospital operating theatres and into established recycling facilities. So while the total NHS hospital waste burden is around 600,000 tonnes per annum, nearly a third of this is generated in theatres, 40% of which is estimated to be recyclable. Current hospital procedures dictate that all waste generated in theatre is classified as clinical waste. And most of this waste is packaging materials, which by definition is single use. In addition, there's a proportion of unused items such as bowls, kidney dishes and trays opened as part of procedure packs or simply unused that are added to the clinical waste burden due to a lack of due process to re-sterilise and reuse. This means that over 69,000 tonnes of recyclable waste is routinely being sent for incineration every year at significant cost to the NHS budgets as well as the environment. So while it's understood that medical practice could not perform at such high levels without the superior performance characteristics of plastics, this linear economy could easily be transformed into a circular one by understanding and then addressing the barriers imposed by the processing of waste in NHS hospitals. So we've learned that the segregation of waste streams in the NHS is largely informed by its place of origin, such as clinical waste from theatres. Additionally, bins allocated in departments will dictate the type of waste streams that items must be consigned to. And it's NHS policy that once waste is sealed in a bag, no second sorting can take place, therefore irrevocably consigning recyclable waste to incineration. It's also important to understand that clinical staff have neither the training, facilities or capacity to sort waste, so that's not what they're there for. So looking at the primary barriers to recycling waste from theatres, the biggest issue to address by far is sorting at point of generation. So is the item paper, is it plastic, is it composite? It's not always easy to tell, especially with films and coated paper and cards. Is it recyclable? There are very few recycling labels on packaging, and where they exist, they're very hard to find or even understand. Is the waste clean? The risk of infection in theatres is very high, where bodily fluids may contaminate waste, even when it's not been in contact with a patient. And also there's an entrenched risk-averse culture that encourages the use of clinical waste for all waste output from theatres. So while COVID has driven an extreme culture of infection control, which in turn has informed the SOPs in theatres, the subsequent relaxation of these SOPs has provided an opportunity for theatre and waste managers to revisit protocols and align to the new NHS Net Zero Green NHS targets and invite projects such as ours to discover a route out of theatre for recyclable waste. So our challenge to create a safe route to divert this new-to-market waste stream away from clinical waste and incineration started with an audit that would analyse typical waste streams produced by theatres, where we found that by weight, 2/3 of the waste that we saw was indeed recyclable, with rigid plastics comprising 15% of the total. This could potentially equate to a conservative 10,500 tonnes of just PP and PET across the NHS every year being recovered and recycled. Our audit confirmed the types of volumes of waste produced in theatres across a wide range of different procedures. Because we engage with sustainability groups in the NHS on the basis of data sharing, we improved engagement and also delivered valuable data to both the project and NHS trusts that have supported us. So this reciprocal relationship has been key to understanding the waste journey from suppliers to theatres and then to ultimate destinations, including where potential barriers and opportunities exist. So once the cultural policy and compliance issues have been navigated, the redirected waste needs to be rendered safe in line with the Health Technical Memorandum guidance. Here I've highlighted the sections that we needed to satisfy. So item A, to demonstrate the ability to reduce the number of infectious organisms present in the waste to a level at which no additional precautions are needed to protect workers or the public against infection from the waste. And C, to render all clinical waste unusable and unrecognisable as clinical waste. So our project addressed the two requirements of contamination and rendering unusable independently. To remove the risk of pathogens entering the recycling waste streams, we've created the Medicycle prototype, seen here, to shred and irradiate waste using UVC light, delivering a commercially acceptable recyclate that can enter an established market. The diversion of waste stream at point of waste generation will allow established NHS protocols to remain largely unchanged, and commercial operations can benefit from the new-to-market waste stream of premium and consistent quality. Shredding reduces the volume into an acceptable format for processing and satisfies the HTM requirement to make it unusable and unrecognisable. While UVC was identified as the optimum sterilisation medium, as it will remove any risk of infection in the waste stream whilst preserving the integrity of the plastics, i.e. there's no added chemicals, no heat degradation, that we may require additional processing and costs. The big problem of sorting has been addressed by integrating a small-scale NIR spectroscopy technology that can identify polymers by type to separate PP and PET, and also non-recyclable waste that can be reclassified into general waste. A simple light ID system with confidence levels will support accurate sorting to deliver quality, uncontaminated resource for reprocessing. And by focusing on specific waste streams from clinical areas, familiar items present themselves for sorting, such as this iGel cradle, which is part of the packaging for a routine device used in almost all general anaesthetics at a rate of about 3 million per annum. So whilst waste management confirm that no waste stream is actually tested for levels of contamination, they would need a certifiable process to ensure the risk of pathogen was removed to enable the theatre waste to move to a recycling stream. The testing regime and results have evidenced that the process works well and to a high standard. So here you see the green line initially is very high. These are our control samples, and then it's almost consistently low all the way across for PP, and we see a little bit of variance with the PET, but all at a very low standard. So samples inoculated with a spore-forming biological indicator were tested across a range of exposures, and we found that rigid PP and PET evidenced a kill rate of 99.7 and 90.4% of colony-forming units, respectively, and Tyvek film performed a kill rate of 98.8%. So, and also the natural characteristics such as the bacteriostatic nature of PET and the optical properties of PP have evidenced that how these should be treated independently to optimise sterilisation results and maintain integrity. So a pilot project as yet unfunded to navigate the best route of waste from theatres will inform how waste can be processed on site for each trust in modified vehicles, reducing the miles travelled. And becoming part of the trust's waste management team, we can target specific departments to reduce contamination risks upstream of the sterilisation process standardise the waste streams and support training and education initiatives. Delivering directly to reprocessors clean, high-quality recyclate and aligning with established NHS protocols, we can implement a low-impact, low-friction, disruptive technology that will address and satisfy the genuine personal desires to recycle, PPN and PPT requirements, NHS net zero and greener NHS targets, and ultimately make a bit of money. So Medicycle will attract 2 revenue streams. First, we will charge for removal of waste from NHS sites. This will be less than clinical waste, but more than recycling costs to be negotiated. And second, we will sell top quality, new to market recyclate to reprocessors at market prices. So at scale, these revenue streams can be commercially viable to support a business and deliver a return on investment for Innovate. So by addressing the practical and cultural barriers, we have evidenced how we can, with the support of NHS theatre and waste management staff, move from the position of no to no because, and we find out what the problems are, to yes if a set of conditions are met, to yes when a plan is in place, to finally yes. So I think you'll agree that this is perhaps the linear model that we can all live with. Thank you.
Thanks, Bev. Again, this was a great one for kind of just realising the value of some things which sort of go into hospitals and never ever get used, but just end up in those yellow bags. It's a sort of seems a real shame of the value that they could actually be brought back to the NHS, let alone the cost they're paying at the moment. So any quick questions for Bev? Otherwise, I'll bring everybody back and we'll have lots of questions. Great. From Britvic at the back.
Yeah, just a quick question on the PET and polypropylene that has been UV clean. Is it cost competitive with the recycled, I guess, non-food grade PET from the regular recycled stream?
Cost competitive in what way? Sort of the actual process of recycling?
The final price of the flake or however it's sold on.
Yeah, because the flake, because the quality of the plastics in the first place is very high quality. It's virtually all, well, it is all virgin material. So we're dealing with a high quality resource that we need to maintain the integrity of through to the flake that we can then sell on to reprocessors, so that we can be confident that what we're delivering is top quality, and that so therefore we can demand a reasonable market price. Okay.
Great. I think, well, we've got about sort of 15 minutes to sort of have some final discussions and then sort of do a wrap up. So just as Bev's walking away, I wondered if, Bev, do you want to come back with everybody else? Smith, is it worth getting the chairs out? Make you sit down. Makes it seem like more of a panel and less of a grilling. Yeah, it's fine. I'm going to drive all the way home, so actually standing up is a good thing, isn't it? Great. So any questions generally for this sort of topic of sort of SMEs getting involved in the space, or specifically on sort of the challenges that that were encountered? Thank you.
It looks all you are really focused on specific problem. So which one is important is identify a problem, identify the market on this technology push is important to get this kind of product.
I think that's quite an interesting one when we talk about kind of where do SMEs fit into the whole system, because we get some businesses who are very focused on already having kind of a very sustainable product that might have come out of some sustainability things. So obviously, like sort of with Hexigone, you know, they're already trying to help with the kind of longer in use aspect of metals and also some of the toxicity things. And so it's almost kind of a bit of a no-brainer, almost kind of adding on the circularity aspect. But for others, you know, you can just be in a market and you go, right, I hear that this is a big driver for some of our customers, or just generally, how do I get involved? You know, so it comes from both. But does anyone have any specific responses on, you know, where you see this as an opportunity or something you've kind of got to acting as a threat?
I think being a polymer business, we basically need to address the reuse of our material. So there are two things. First, the reuse of our material, but also the big amount of landfill that we are creating with our process at the moment. So it's a no-brainer that we really need to reuse that.
For our case, as I said, from the recycling industry, that we were talking about with the hub that was mainly on lithium-ion batteries. We were talking about something completely different. But then discussion came, you have expertise in ultrasound, do you think you can do here and then? There has been some detailed discussion, we have been introduced to the problem. So now we understood that we can have our contribution to this really classic and unknown problem, which is recycling lithium-ion batteries.
Hello, I'm Zina Skufa from Johnson Matthey. I have a question for Rheon, actually. I was wondering, this need for finding a circular solution, a recycling solution for your products, how much did it come from your customers and how much did it come from your internal?
So it came initially from us internally, because of the markets we're currently looking at. However, now that we are going more towards the apparel market, there are also certain circularity requirements from customers there. However, that's a little bit vague at the moment, so there is no real regulatory requirement, or different customers require different things, and they're not sure what they want exactly. So they want to have a green product, but the definition of green is a little bit difficult sometimes to really grasp.
Jonathan?
And one thing that struck me from the presentation, actually, quite a few of you face issues around end of waste or legislation. And I think particularly for Rheon, it seems to be a problem with exporting and importing that forces you to look at different solutions. So maybe what do you need, or did you have anything that needs to simplify this kind of framework so that most innovations can happen maybe more quickly?
So, yes, I think for the injection molding solution, the solution we currently have is actually working really well, because we needed a 3D printing capability. We wanted to have it for a long time because it really shortens our whole design cycle considerably. So reusing the material for 3D printing is actually a really, really good solution for us. In film, we may face this challenge. We are currently looking into the logistics of it, but with our film waste, it's initially a technical problem. So how do we actually reuse that? Once this is solved, yes, we will come to this import-export problem again.
Any more comments on import-export?
Can you classify it as not waste?
Yeah.
That works as easily.
No, so the only way to classify it as not waste would be to recompound it into pellets, but then you use actually quite a lot of energy in the compounding process. So there is a way around it, basically, without importing or exporting, but that depends on what technical solution we actually find to the problem.
I mean, this often obviously comes up in the circular economy programs of where are those policy barriers on sort of getting things classified as waste or not waste. I think it's something we hopefully, kind of the NICER program as a whole, can sort of really hone in on. Where is it specifically problems, or is it just a general thing? I think just saying a free-for-all on let's not call anything waste is how we end up just exporting all our problems elsewhere. So there's got to be a middle ground somewhere. So yeah, hopefully some of the advice coming out of NICER can really target that.
I also don't think it depends, like we can classify it, for example, as non-waste, or a lot of polymer producers can classify it as non-waste. It's more the authorities who take it, whether they classify it as waste or not. I think also how it looks makes a difference probably. But yeah, I think there's no international standard of what is waste and what is not waste. So something that the UK may not classify as waste may be classified as waste elsewhere.
I get the impression that you're pretty well established SMEs to begin with anyway. But the question is how do you go about, in your case, capitalising something like this? Because you're on a new venture. Or if you're an SME, a startup SME, how would you look at capitalising such a big transition? That's for anyone.
I think that's the next phase, to be honest.
Yeah.
And the question cropped up earlier. For SMEs, it's very difficult to raise the capital to get the projects going. But working with NICER, it gives you more of a credibility when you're approaching funders. But I think it's been a long time, it's always been there, that with Innovate, projects are great, science is great. How do you help the SME to really kickstart it?
Yeah.
It's very difficult.
I mean, obviously, we don't just provide government funded things. We also do sort of things like investor partnerships and some other things where we try and bring in private investors to educate the other investors about where there are really good opportunities. So we kind of see there's definitely a point there. But yeah, I think it is a challenge to sort of get some of these things proven and to sort of find your space. Yeah. Any more questions? I think good, but no, I mean, thank you all. I mean, I think you've all sort of would say it's been I hope you'd all say it's been sort of a good opportunity to kind of test some of these ideas within NICER. But yeah, it's really interesting just to see how we can get that learning out into the programme and sort of take some of these sort of real world examples. And the hub itself, I don't know if it's kind of been sort of widely communicated, has got a sort of a knowledge centre there, which is sort of getting a bit of a sort of kick towards getting a lot more case studies and examples on there. So all of our SME projects will have a case study there soon, which will have sort of information just at the basic level, but also where they've got specific examples on sometimes things like policy barriers. We've got given the kind of the opportunity just to pull those out, so it's a bit easier to see some of the cross-sector learning. But also, you know, obviously with Uvamed as well, we've got NHS England on the advisory board for NICER, so we're able to kind of get some more discussions going there, just so they can see the scale of the problem and see some of the opportunities. So, yeah, hopefully this programme leads to lots more on the back of it. So, unless there's anything final, can I say a final thank you to our businesses, SMEs and speakers. Okay. So we've got a final few things just before I can let you loose into networking at 5 o'clock. So some of the things we wanted to flag. So this is kind of on behalf of my KTN colleagues who couldn't be here today. A couple of them weren't able to come. But some of you have been involved in this. So I just wanted to flag what's going on. So within Innovate UK KTN, we have Circular Economy Innovation Network. So this is an example of where we kind of say it's all very well giving grants to individual projects, but how can we use sort of money strategically to bring together relevant companies on a specific topic and really sort of map out where some of the opportunities, gaps, action plans might be. So we have some specific ones in the circular economy space at the moment. So there's one on transforming industrial waste gases to chemicals, another one on wool, as Nick mentioned, and one on aluminium. And there's going to be some different ones in the coming years to come. So Michael Burnett was going to be here just to talk in a bit more detail about this, but he said, here's a code, you can go and read the report because it's issued last week. So anyone who's interested in this space of how do we get from carbon monoxide, carbon dioxide into useful chemicals, that particular network has launched the action plan, so they would love, again, more feedback if you haven't already been involved. But I appreciate we've tried to make sure that the NICER Centre is obviously involved in here because there's a really big overlap with some of the road mapping work you're doing. So any more information you'd like on that, please do contact Michael directly or just go and have a look at the report. So if this got your appetite going for funding opportunities, I know funding came up big there, but I appreciate we're business-led funding. So if academics want funding here, you've got to find the business with the problem that you can help support. You can't lead on these opportunities. So if you're looking generally about opportunities in this space, I would say sign up to the Innovate UK KTN website and the newsletter, because just because of the timing of kind of spending review cycles, there is a lot of funding available at the moment that has to be spent in the next 2 years. So it does come in waves. We would prefer it to be more sort of general and longer term, but this is the way it is. So there's a lot of things available at the moment. Specifically, when I mentioned about the materials and manufacturing vision for 2050, on the back of that, we've got some specific funding across these areas. So we've got funding under the title of Resource Efficiency for Materials and Manufacturing, Reform, which is up to £12 million of funding, which is opening this week for 8 weeks. And that's collaborative R&D scale projects. We've also got a very specific one on sustainable bio-based materials and manufacture, which is in association with EPSRC and BBSRC. So that one does have a bit more of a kind of closer to academia level of innovation there. And what we're kind of saying on here is, with reference back to our vision, what we're focusing here is on these core areas. So it's looking at sort of the new materials, bringing in circularity, bringing in design, production. It's not focusing on the enabling areas, but obviously you may have reference to kind of the energy aspects, the regulations and skills within those projects. But it's very much this joining the dots, collaboration and being encouraged, and actually looking almost innovatively to who you partner with. We've talked about some of the business model challenges here. It may be partnering with someone who can provide kind of the financing model to actually do leasing of your product if you don't want to do that directly. So things like that might come into an interesting project in this space. For more information on those, more QR codes or short links here. So these are links to further information on the Reform funding, further information on the SUSBio. But of note, next week, if you're not on Easter holidays, then in London we've got an in-person event which is bringing together lots of speakers on this topic, a bit more information about the competitions, but again, trying to get some innovative collaborations going, so thinking outside your bubbles. And if you want to talk through any funding proposals, then Michael's the specific contact for chemicals. If you're kind of going into bio, there's a whole bio team at KTN as well. And we'd really encourage that. I think there is quite a good correlation between companies and project teams who get in touch with the KTN prior to submitting their application than those who just go, I've done this before, or I understand this, I'll give it a go. Because every competition has a nuance about it, and they're a good independent sort of point of view on things. So they can review applications, although there's probably a limit to the capacity and how many. Do take advantage of that. Also just flagging, maybe not just for Djelloul, but if anybody else is kind of interested in things to do with critical materials supply chains and specifically rare earth elements, we also have a £15 million new programme called Climates, which is about looking at the circularity of rare earth elements. So there's lots of reports available if you just Google Climates Innovate that will give you information on what that's covering. And they've got their competition webinar next week for funding in this space, and they've got an in-person specific event on the 19th of April. And lots of things there showing government support for this area. So just a general thank you to that space.